see your presentation. So, thank you. Welcome to everyone to this seminar of this week. So this week we have invited to Dr. Daniel Passeri from University of Rome Sapienza. Dr. Passeri, you can check his Google Scholar, has an H index of 29 and more than 2,050 and 500 citation. So he's a very recognized researcher in his area of research. So welcome, Dr. Daniel Passeri, so we can hear your speak.
Thank you very much for your very kind presentation. I must say that I'm very, very honored to be here this afternoon for you, this evening for me. And I would like to thank, first of all, Professor Francisco Flores. This invitation basically comes from him. I was thinking about what can I share with you about my research. Just let me. The topic I choose is quantitative issues in magnetic force microscopy. But more interesting that it is the subtitle, When Problems Are the Beginning of Solutions. Just let me explain why I choose this topic, because my research activity has been focused from my PhD to now, so for almost 20 years, on atomic force microscopy, and in particular on methods based on atomic force microscopy for the characterization of different physical properties like mechanical, magnetic, electric, and so on at the nanoscale. So my main issue was, okay, I would like to share with you something about magnetic force microscopy and the characterization of magnetic properties at the nanoscale. But really my question was, can this topic be interesting for students and young scientists, I hope, who are not involved in magnetic force microscopy? Well, of course, I hope all of you is very interested in magnetic force microscopy, but I really fear is not so, is not the case. So I thought that basically I would like to speak about something which not always, how can I say, older senior scientists speak about. So during your research, you will browse in the scientific literature, and you will you found, I'm sure, many papers which report many successes of the author. So every experiment is successful, every data perfectly fits the model, so everything is nice, but no one generally will tell you anything about their failures. Really, I must say that maybe I have not been so lucky in my life, but what I must say that scientific research is made mostly, let's say, 80%, 90% of failures. And of course, not to put you down too much, we will have some success, which pay us back for all our sacrifices. So I would like in this seminar to share my personal experience, of course, with magnetic force microscopy, but I would like to share you the problems I encountered, which I must say that were the best things that happened to me, because every problem was the starting point to find solutions. So just the summary of this presentation, I would like give you just a short introduction to magnetic force microscopy. Maybe not all of you knows something about this. And I would like to give you some examples, though I choose to give a focus on biomaterials and biosystems, but not for any special reason. And the most interesting thing when you do measurements using scanning probe microscopy is quantitative characterization. So the successes, but also the limitations. So we will address in particular the problem of electrostatic artifacts. Some possible solutions, let me call them outstanding. I would like to anticipate that outstanding solutions are not those we found, but are those other groups found. And our solution, which is much simpler, and some results and some perspectives. So, and then, okay, I will move to the conclusions. So, let me introduce, of course, you know probably that magnetic nanomaterials have been proposed, are currently being proposed for many, many technological applications, like, I don't know, nanobiotechnologies, for instance, magnetic imaging, active drug delivery, theranostic applications, and so on. Of course, as as for all the applications of materials, also to apply nanomaterials, you need the capability to characterize their properties, so in particular the magnetic properties at the nanoscale. Of course, ideally resolving each individual nanomaterial. Why? Because there are in magnetic people studying magnetism of materials, there are some quantitative devices like the superconducting quantum interference device, magnetometry, or vibrating sample magnetometry, and they can give you for instance, the magnetization of the material, the hysteresis curves of your material, but it's averaged on the sample. So imagine you have many, many, many particles. This is an average on all the particles, while ideally one would like to address the single unit of nanomaterial. Conversely, magnetic force microscopy is a method very, 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 very widespread, because it's a simple method based on scanning probe microscopy, like atomic force microscopy, let's say. And atomic force microscopy nowadays is very, very, very widespread. So you can find it almost everywhere. And basically everyone who has an atomic force microscope can also perform magnetic force microscopy. Just to summarize, in atomic force microscopy, you measure. I should have the, let me see. You should have the you can acquire the topography of your sample. So the surface, you can reconstruct the surface of your sample just by moving and scanning the surface using a very sharp tip. Of course, you have an object which is a very sharp tip, which goes very close to the sample. And imagine you are touching your sample at the nanoscale. You may decide to measure something like electric properties, magnetic properties, and so on. So in particular, in currently used magnetic force microscopy, you have a two-pass technique. So in the first pass, I hope you can see the pointer. The tip scans the surface, and so the system acquires the profile. There is a second pass, so each line is scanned a second time. If the liftate is fixed, so a profile is followed at a certain distance from the surface. The tip, the cantilever to which the tip is attached is oscillating. You have a laser which can monitor the deflection of the cantilever. So on the photodiode, on the detector, you acquire an oscillating signal. So the deflection signal is oscillating. And you can measure you can measure the shift in the resonance frequency, or by fixing the excitation frequency, the phase shift. The nice result is that, for instance, let's focus on the phase shift. The phase shift is proportional to this parameter, which is the derivative of the tip sample force, the vertical derivative. So it's the gradient of the interaction force between the tip and the sample. Of course, if you choose a tip which is coated with a magnetic film, and the sample is magnetic, the tip sample interaction is a magnetic force. So this phase shift gives you a signal which is proportional to the gradient of the magnetic force corresponding to the magnetic interaction between the tip and the sample. Now, this is an example. I like this kind of example very much because a bit old-fashioned. I fear not all of you young students know what a floppy disk is. Probably someone, I hope someone of you still saw them. They were the grandfathers of our USB memories. So they were disks with magnetic domains. This is the topography of the surface of a piece of floppy disk. Basically, I obtain this sample opening a floppy disk and cutting the disk. If you see the topography, okay, you have a certain roughness, but you don't have any information. This is the magnetic phase shift. You see here, this area is the area with the magnetic domains of your sample. So you see something which is not in the topography. So you are watching something of your sample beyond the simple topography. Now, just some examples. This is an example of recording media. So again, the floppy disk. Here, it's topography and magnetic signal from magnetic nanoparticles. So they were iron oxide nanoparticles. We will discuss a bit more about them later. Here there were some systems made of vesicles with some magnetic nanoparticles inside. And here there were cells, two different kind of cells, loaded with magnetic nanoparticles. Also, in this case, it was magnetite. Just quickly moving on some results, you see here there were some microglia cells. This is the optical microscopy. You see here inside this dark region, which is an aggregate of magnetic nanoparticles. You see here in the magnetic signal, you see that these nanoparticles are revealed. So you are watching something which is below the surface. This is a nice result from a group very active in the States in magnetic force microscopy. Basically, they use the magnetic force microscopy to detect the presence of iron-rich regions in sections of Sprague-Dawley rats. Another, of course, these are qualitative results. So basically, you can see the nanomaterials and that's it. But here, there is another nice result, which is a quantitative detection. Basically, I'm not going to go too deep into this. The same group from the States, they could distinguish between apoferritin and ferritin, which are the same molecule, but ferritin contains an iron core. So this was this very low phase shift corresponds to apoferritin, so without the iron core, while this higher contrast is the ferritin, and this higher phase shift is due to the iron content. Another nice result, which is not from biological system, of course, it is this result, which is a set of magnetic nanowires vertically aligned into a polymer and then cut. What the author did was to vary the magnetic field and simply say, okay, as these nanowires can have an up or down magnetization. If I count the dark and the bright spots corresponding to the heads, here we are watching the sample in this way, so we are watching from this. If I look and I count the dark and the bright spots, I can try to see, to define the contrast as the difference between the number of bright, which means up-oriented nanowires, and dark, which means down-oriented. And the nice result was that while the authors obtained the points here, while the continuous line is the result obtained using a macroscopical system. So this result is very nice because basically you have a link between the behavior of nanometrical sized domains with the macroscopic behavior. Now, let's up to now, this is exactly what I tell you before. You watch, you read the papers by other groups. Everything works. Everything is perfect. We said, okay, let's start with the magnetic recording media. For this kind of materials, magnetic force microscopy works perfectly. You see, for instance, just an example. According to the model, you expect this profile, this is the floppy, with a tip vertically magnetized. You expect this profile with the tip horizontally magnetized, and the experimental results fit very well with the theory. So, for instance, we try to say, okay, let's see if we can measure, for instance, the thickness of films. Here there were bacteria on magnetic substrates. And for instance, here you have this colony. We measure the phase shifting corresponding on the points A, B, C, and D, and you find them here. If you look at these points, the phase, the absolute phase, doesn't seem to have any sense. But if you measure the contrast, you obtain the open squares are the contrast on the floppy, while the dots are the contrast, so C, phase in C minus phase in D, in correspondence of the film. You see there is a very good matching, which means that basically I can measure. Okay, in this case we could measure the height of the film because we had these edges. But imagine you don't have this edge, but you have a uniform film. You can, from a graph like this, you can calculate the thickness of your film. Just something you should note is that somehow the differences between phases seem more in agreement with the theoretical model. Here, sorry, I didn't mention it. This dot line is the theoretical model. It's an exponential decay. So the phase difference seems better than the absolute value of the phases. So, of course, I must swear that when you have a microscope and you can perform a magnetic force microscopy, you cannot measure floppy disk forever. At a certain point, the your friend working in the lab close to yours, maybe they prepare magnetic nanoparticles, and also they come to you and say, can you measure something with my nanoparticles? Yes, why not, we say. But, and of course, we had the same the same issue, and they ask us, okay, can you measure something about our particles? This is an example. You have here the topography and here the phase. And the problem was, okay, but what can we measure on nanomaterials? Of course, if I have a nanomaterial, I can measure the diameter of the nanomaterial. And I can measure the phase shift. So what I can measure is the phase shift, for instance, as a function of some parameter. Of course, the diameter of the nanomaterial, but also, for instance, the distance at which you are performing your it's Alexa, stop. Sorry, it's my children note. Anyway, you can measure it as a function of the distance between the tip and the sample, which is the leaftate. And maybe you can add an external magnetic field. And if you add an external magnetic field, you can measure magnetic properties of your samples as in presence of a magnetic field. So we said, okay, everything works perfectly. Let's go. At the beginning, it's fantastic. You see, this is the profile you expect is the red one. This is the profile you expect for the phase shift. Well, it's quite good, the experimental results. So everything works very well. Of course, we started with very, very small particle, magnetoferritin, which is ferritin molecules where the iron core is replaced by an iron oxide core. And we obtained those phase shift. Note that dark phase shift means attractive. So in this case, there were not an external magnetic field. The magnetic field was produced by the tip, so the tip attracted the iron core. And this is the model, which is the standard model you would expect for two dipoles interacting, and it seems quite good, the result. But, oh, sorry. But let's, these are very simple models. So we have those very small nanoparticles. We are using a two magnetic dipole model. Seems very, very well working, but we start to observe something strange. These are iron nanoparticles, the topography. You see, at low leaftate, everything seems correct. Okay, I have dark nanoparticles, which means here there was a magnetic field, but these are details. In any case, there was a attraction between the tip and the nanoparticles. When you increase the liftate, this contrast disappears, which somehow is reasonable, because if you go too far, you cannot feel the magnetic field anymore. But if you increase again D8, those particles starts to be bright, which is really a completely nonsense. It seems that at a certain point nanoparticles reverse their magnetization, so they are repulsive. I don't know. But the problems were much more than this, because we did the statistics on many nanoparticles. You see, this is the phase shift depending on the diameter. And you see, wow, there is a very good linear relation between the phase shift and the diameter of the nanoparticles. Oh, sorry. But really is not, this model does not foresee a linear behavior. Here you have the cube of the diameter. And these were some, and the most upsetting thing was that we repeated this experiment many times, and they were always coherent, but always contradicting our simple model. We obtained this linear relation, y is not foreseen. Here, okay, here there is the decay we would expect, because this is as a function of the liftate, and so here there is the fifth power, and is 1 divided by this. But why this strange result? This is not easily described. Really, even with, I don't want to stress it too much, but really with those curves, we could at the beginning set up a system to measure the diameter of nanoparticles inside vesicles. And it seemed to work. The problem was that basically we said, okay, I don't understand why the behavior is this one. However, let's create a phenomenological calibration, and it's okay. So the measurements of the diameter of nanoparticles inside the vesicles were correct, more or less. But as you may understand, it's quite frustrating to have a phenomenological calibration which is not based on models to describe the tip-sample interaction. Of course, the first thing you do, let's create more comprehensive models. For instance, we started thinking about the fact that the tip was without the magnetic coating, so there was just a ring, and so on. We could fit the results, but when you have many parameters free, you can fit almost everything. The problem is that the geometrical parameters, like the radius of the tip, were quite unrealistic. Like we obtained a radius which was 10 microns, while the tip was expected to be 50, 100 nanometers. So that was not a good approach. But we start understanding which the problem was, when we said, okay, let's measure the phase shift, the magnetic phase shift, using a magnetic nanoparticle, using a tip which was not magnetized. And you observe here bright contrast, bright but lower contrast. So you see a positive phase shift. Here we realize that this is an artifact, and this was quite upsetting because you see plenty of papers about people, researchers, publishing results on magnetic images using MFM on nanoparticles. Many of them, I can assure you, are fake. They are not magnetic signals. The problem is that there is an electrostatic artifacts. Electrostatic artifacts are due to the fact that when you are on a flat substrate, you have this distance between the tip and the sample. But when you are on a nanoparticle, okay, this distance is the same, but the average distance from the sample is bigger. So you have a change in the capacitance. So there was a very, 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 very clever intuition by Professor Agustina Asenjo from the Spain Council of Research. And they said, okay, when you have electrostatic artifacts, you have a force. The force depends on the tip sample voltage. But if some of you happen to some of you to work with this, in atomic force microscopy, you can create a system to measure the tip sample voltage, which is the so-called Kelvin probe force microscopy. And so what they did was, okay, this is the topography. This is the standard magnetic force image. Now let's measure the surface potential. If you measure the surface potential, you can apply at every point of the image a potential, an opposite potential, so that locally the tip sample potential is 0. In this case, you nullify the electrostatic artifacts and you obtain the truly magnetic image. This is for a wire, a magnetic wire. This is for a more complex magnetic material. So this is a very clever solution. The problem is that currently no one of the producers of magnetic force microscopy allow you to have this system because they do not include in their systems. So we thought about another solution. So basically we made an electromagnet. This electromagnet is creating a magnetic field here. Now, if we put again the floppy disk, what we did was to apply a certain voltage and then switch it off. In the end, you measure the contrast on the floppy. If you report here the contrast as a function of the applied magnetic field which is applied and then removed, you have a curve which is the remanent magnetization curve of the tip. Remanent because what remains after the magnetic field is off. So you can measure these values, which is the remanent coercivity of the tip. So the idea was, okay, first let me measure a standard magnetic force microscopy. Standard magnetic force microscopy gives you a signal which is the real magnetic signal plus the electrostatic signal. Then we apply the remanent coercivity. So we apply the magnetic field corresponding to the remanent coercivity. We switched it off, and so we demagnetize the tip. And we repeat the scanning. If we repeat the scanning as we have switched off the magnetization, the signal is only the electrostatic one. And so you can simply subtract the second to the first, and you obtain the pure magnetization signal. And this was quite a surprise for us, because, for instance, this is a floppy with this is the topography with this big thing, this big particle. Standard magnetic force microscopy is this one. So you have a contrast in correspondence to the particle. So you could think, okay, the particle is a magnetic particle. But if you switch off the magnetization, you obtain the electrostatic image. And so you obtain that the contrast is purely electrostatic. If you subtract, you obtain this one, which is the real magnetization signal. Okay, for this case of the floppy is not interesting at all, but is much more interesting in the case of nanoparticles, because again, we have the topography, the standard magnetic force microscopy, the image with the demagnetized tip. You see all the nanoparticles are bright as expected, and this is the subtraction. And we understood that this was good because if you consider the quantitative phase, this is the standard magnetic phase. Basically, this is meaningless. You see, the beginning is dark, then it's bright, here is almost zero. This is the standard, is the electrostatic image. If you take this one and you subtract this one, you obtain these dots. This is for a single particle as a function of the liftate. And you see that if you take again the model of the two dipoles, which is the simplest model you can think about, the model fits very well with the results. Also for particles with different diameters. So basically, in this result, with these results, we realized that in this case, it was not the model, the model that was wrong. It was the experiment. And what we did with this, for instance, we tried on magnetic nanoparticles, but applying also a small magnetic field. And the nice results was that we could obtain these magnetization curves, which are the magnetization curve for a specific nanoparticle. So this nanoparticle had a diameter of 32 nanometers, 31, 26, 21, 18. The nice result was that we plotted the calculated magnetization. Okay, this suffered from some approximation, and I don't want to discuss it too much. but also the coercivity. And it's very nice that even if the nanoparticles are very small, here you have a coercivity, which decreases here. So here you are the switching in correspondence to about 20 nanometers, the switch from a ferromagnetic behavior to a superparamagnetic behavior. I see that I'm wasting too much of your time, so let me just reach the conclusion. Another application, we try to measure the thickness of, we had the core shell nanoparticles, so a magnetic core and a not magnetic shell. And we measure indirectly, of course, the shell of magnetic nanoparticles. For instance, in this case, we had these nanoparticles of cobalt, which were directly synthesized on substrate, so we couldn't remove. And we measured the value of the magnetization and also the thickness of the non-magnetic shell. The non-magnetic shell is due to the presence of the formation of cobalt oxide or cobalt hydroxide. So, just to conclude, I try to convince you that, no, it's not try to convince, this is very obvious that magnetic force microscopy allows you the qualitative visualization of magnetic properties at nanoscale, but also quantitative. And I try to convince you that these quantitative measurements are more often than not limited by the presence of electrostatic artifacts, which are most relevant in the case of nano-sized material. But if you remove electrostatic artifacts, it seems that even very simple models work. So everything seems to go as it must be. I reported two of our applications, so the thickness on not magnetic coating of core shell nanoparticles and the magnetization curves of isolated single nanoparticles. So we selected in the image that nanoparticle and we obtain its magnetization curve. So now the last thing which is left is to thank you for your kind attention.
Thank you, Daniel, for your presentation. It seems very interesting. So now we have time for a few questions of the public. We have now Dr. Francisco Javier.
Yes, thank you. Thank you, Daniel. I have two questions. How do you magnetize the proof without losing the region to be analyzed?
Sorry, I'm making some mistakes with this. Sorry, can you repeat the question?
Yes. How do you perform the magnetization of the proof?
Mm-hmm. The magnetization was made directly on the sample. So the coil we did was used as the substrate, as the basement on which the sample was applied. So basically, what happened was that we could go with the tip on an area. We lift the tip just the lift height needed to avoid crashes, and then playing with the voltage, we apply the magnetic field and we magnetized and demagnetized the tip in situ.
Oh, okay.
So without needing, no, otherwise it would be impossible to remove the tip and then find again the same position. Of course, it will be impossible.
Yeah,
You did perfectly right.
And the second question is do you perform when you lose the magnetization of the proof, do you perform a magnetic or electrostatic measurement?
When you remove the magnetization, so you have a tip which is, for instance, a cobalt chromium tip, but not magnetized, like the one you receive when you buy it from the vendor. In that case, you have only electrostatic images, because they are independent from the magnetization, of course.
Okay, thank you. Thank you, Daniel.
You're very welcome.
We have another question from Dr. Ulises Salazar.
Thank you so much, Hanani. Thank you so much, Professor Daniel, for this very clear and didactic talk. I have a question. You succeed to measure very small nanoparticles. So is it possible to measure the superparamagnetic state with your system? Because we have very small particles, and at room temperature it's very easy to switch the magnetic momentum. So is it possible? Or have you tried?
In the case of we used very small superparamagnetic, iron oxide nanoparticles. Those iron oxide nanoparticles had a range from those we measured were from 30 and some to down to 18, 15 or so. So we think, of course, we believe we observed the superparamagnetic switch because basically I should share the screen again. But basically, what we observed was that we had a small hysteresis loop, even for instance for the 30 nanometer nanoparticle, while for instance for the 18 nanoparticle, as we decreased the dimension, we observed the shrinking of the hysteresis loop, and the only we observed a small hysteresis loop in correspondence to nanoparticle of 21 nanometers, and we didn't observe it in that of 18 nanometers. So we believe we test the ranges between ferromagnetic and superparamagnetic. Unfortunately, we couldn't go further on these experiments.
Okay. Thank you so much.
You're welcome.
Any other question from the public? So I have a question. You mentioned that the papers that I already published about the magnetic measurements are basically wrong because they
no. Please,
well,
don't,
some of them could be wrong.
So, some of them could be wrong.
Could be wrong.
In my personal opinion.
So, do you recommend to perform all the methodology that you propose for all the samples, or how is that we could be sure that our measurements are right?
Of course, if I should advertise, I should say, no, you must always measure following my method, or the fantastic method by Professor Asenjo, this Spanish woman who is fantastic. You should attend a seminar from her. Basically, I warmly recommend to include her as in your list of seminars. But to be honest, in my experience, you really have problems of electrostatic artifacts when you have a very, very peculiar surface. For instance, in the case of floppy disk, the floppy disk, okay, is rough, but the roughness is almost constant. So, okay, you may have electrostatic artifacts, but they are not really affecting your results. You have the problem of the electrostatic artifacts when you are watching very small nanosize material. If you want to check, an idea is, okay, I don't know if you use an atomic force microscope, but you have your atomic force microscope, you perform a magnetic image, and then you can say, okay, let's maintain the same setup, but let me replace the magnetic tip with a not magnetic one. Like, for instance, if you use a cobalt chromium tip, which is magnetic, you can change the tip and measure magnetic properties using, for instance, the platinum coated tips. In that case, if you see a contrast, this is electrostatic. So in this case, you should say, okay, yes, my measurements are magnetic, but I would personally avoid to say, okay, I measure the magnetic moment of my nanoparticle, which is exactly this one, just this. But if you have a perfectly flat magnetic film, the image you obtain is just magnetic. Okay. Unless you have localized charges. Okay. Which is which was something which drove me crazy with the sample of Professor Flores.
Okay, so I will probably send you some samples to compare with the measurements I made with Professor Flores. just to check.
I tried to convince Oxford to add this the same feature who Professor Asenko has on her instrument. The problem, the instrument was in-house made. I asked Oxford to add, and basically they said, yes, we could basically add it. Maybe you just have to pay something like 20,000 euros.
So like another new AFM.
Yes, basically they say, if you pay me, I will develop this and I will put it on every microscope I will sell. So basically you will spend money to help all the world.
Everyone.
Yes, I say, okay, I will find the money somewhere. I don't know exactly where, but
okay. So do you have any other question? I think we don't have any questions. So we thank you again, Dr. Daniel, for your presentation and to give
us... Let me add just one thing. If any of you is interested in some exchange of students, so if any of you wants to come in Rome, keep in touch and you will be very, 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 very welcome.
Thank you, Dr. Daniel. So we have a few researchers here that maybe take advantage of this collaboration, and also the students can ask to their advisors. So thank you, Dr. Daniel, again. Thank you, everyone, for being present in this seminar.
Thank you very much. Bye.
Thank you.
Have a nice weekend.
Nice weekend to everyone.